In this example, we're going to deal with a couple of vectors relative to a non-standard basis. So we're going to pose two very similar questions here, but we're going to be using them to go one way or another relative to our non-standard basis. So what I'm seeing here is the non-standard basis is going to be comprised of, well, essentially the vector 1, 1, 1 minus the standard basis. So subtracting 1 from the first component would be 0, 1, 1. From the second component would give us 1, 0, 1. And from the third component gives us 1, 1, 0. The first thing that I would like to do is say that if we have a coordinate representation relative to this basis of 2, 4, 8, what I'd like to do is find x relative to the standard basis. So we can interpret this. Let's go ahead and name these three vectors. Let's call them v1, v2, and v3. So the interpretation that we can give to x relative to the basis b is that we are taking 2 of the first vector, so 2v1, 4 of the second vector, 4v2, and 8 of the third vector, and adding them together. Now to actually write this out, this will be 2 times the vector 0, 1, 1, plus 4 times the vector 1, 0, 1, 1, and 8 times the vector 1, 1, 0. To figure out what each of these components will actually be, let's go component by component. For the first component, we'll have 2 times 0 plus 4 times 1 plus 8 times 1. It'll be a total of 12. For the second component, that'll be 2 times 1 plus 4 times 0 plus 8 times 1. For 2 plus 8, that'll be 10. And then finally, for the third component, that'll be 2 times 1 plus 4 times 1 plus 8 times 0. So I just heard a 2 plus 4, that'll be 6. So, according to the standard basis, if we have 12i plus 10j plus 6k, that is the same as saying 2 of these plus 4 of these plus 8 of these. Now, in our second example, we're actually going to flip it around. We're going to say, suppose that we have 2 i's, 4 j's, and 8 k's. What would that representation look relative to this basis? So what we're going to do is find C1, C2, and C3 such that C1 times V1 plus C2 times V2 plus C3 times V3 is equal to the vector 2, 4, 8. Now, using our little shortcut that we can use to set up this process, the augmented matrix would have vector v1 in the first column, vector v2 in the second column, vector v3 in the third column, and we would be augmenting with our vector 2, 4, 8. So in the first column, we put 0, 1, 1. Sorry, that's off camera. So in the first column, we put 0, 1, 1 to represent the first vector. In the second column, we put 1, 0, 1 to represent the second vector. And in the third column, we put 1, 1, 0 to represent the third vector. Now, technically, each of these are actually referring to the values of C1, C2, and C3. We are going to take this down to reduced row echelon form to solve the system. However, rather than doing it by hand, because we are so advanced now, we are going to be able to use our calculators to do so. So we'll position that on the left side of your video, and let's go ahead and enter the matrix menu on the calculator. So first thing I'm going to do is edit my matrix A. I don't really care what was in there from the last use. We are looking for a 3 by 4 entry, or 3 by 4 matrix. First row we read as being 0, 1, 1, 2. The second row is 1, 0, 1, 4. And the third row is 1, 1, 0, 8. I'm going to quit out of the matrix menu, reselect the matrix menu, and select matrix A just to make sure that everything got inputted correctly. And hopefully it's clear to everybody that what we have here is the same as what we had over here. Next, I'm going to re-enter the matrix menu, arrow over to the math column, and select RREF of, re-enter the matrix menu, select matrix A, close your parentheses, press enter, and hope that all goes well. And it looks like things went pretty well. When we take this down to reduced row echelon form, we are arriving at the following matrix. We have the identity matrix to the left of the augment, which is exactly what we would predict for a standard basis. And the augment is 5, 3, -1. Now, in order to interpret this answer, first off, what we're saying is that the representation of W relative to the basis B is the coordinate matrix 5, 3, -1. Now, if we want to verify that this is actually correct, what we could do is calculate 5 times vector v1 plus 3 times vector v2 minus 1 times vector v3 and verify that the result is going to be 2, 4, 8. Now, let me go ahead and copy that out. That'll be 5 times vector v1, which was 0, 1, 1, plus 3 times vector v2, which was 1, 0, 1, minus the vector 1, 1, 0. For the first component, I'm seeing 5 times 0 plus 3 times 1 minus 1. That is 3 minus 2. Or excuse me, 3 minus 1 to get 2. For the second entry, I'm seeing 5 times 1 plus 0 minus 1. And for the third component, that'll be 5 times 1 plus 3 times 1 minus 0. 5 plus 3 minus 0 is indeed 8. And that verifies that our result is correct.